Yes, not enough.
I'm really like that's just so much. Even like
First slide's hot off the press. See you writing
I was writing just then. Just to save all the questions. I don't have that dependency on me.
No, it isn't.
Well, yeah.
I think people are a little bit late, so you might want to wait a few more minutes.
Yeah.
We didn't get around to rounding people up.
Cool.
The latest version I have is 019. Will I be able to follow along?
019. That's probably like 6 months old.
I forgot to pull from GitHub before I could.
I didn't tell anyone what to do, so my fault. Yeah. There's only so much you can do with a type system. So.
What do you mean? It's your incomplete. You can do anything, right?
That's right, yeah. Please do. I think that this pulls 1.5.1 anyway. Keynote quotes.
See, I'm independent enough that when I make slides, I hit the key to get the flat quotes because it bothers me that they're not the actual quote.
20 degrees my hand.
It's getting cold.
I know, don't touch them. I hate you mentioning it, but I don't want
I ran out of keys a long time ago. I'm actually wondering if I can get like an attachment that would give me an extra row of function keys. Because I'm tired of adding more modifier combinations. I want more physical keys.
I don't think the problem is the keyboard. Just a test.
Yeah.
All right, I think we can make a start. Only 10 minutes late. It's okay. So I'm Ambrose. I'm from University of Western Australia, just a student. Not saying I'm employed there or anything, but I'm about to graduate with an honours degree in computer science, and my subject in my dissertation was creating core.typed. It was known as typed Clojure last year, but recently it's been accepted into Clojure contrib, as you can see from the lining and dependency screen. So if you want to follow along and you're lucky enough to have internet, chuck this in your lining and it will pull it down. But this workshop's kind of about me, so, you're gonna have to check out what I'm gonna do. Okay, a bit of background on core.typed. You didn't see the talk yesterday, so core.typed is an optional type checker for Clojure. It's a particular kind of type checker called a gradual type checker, and its ancestry is typed racket, which is gradual typing for racket. And gradual typing basically means that we've got typed and untyped code in the same program, and gradual typing can also accommodate some ways of different ways of ensuring interaction between untyped and typed code are still sound at runtime. So core.typed implements the static checking, has no runtime checking. So yeah, it might have been developed for academic in an academic environment, but it's definitely intended for use. Typed racket is definitely practical, and I've copied all of typed racket and made it a bit more Clojure-y. And yeah, so I think it's getting there. It's not quite production ready, but I'm not sure if the Google Summer of Code projects for Clojure have been announced yet, but I have submitted one for core.typed to improve documentation and basically get it up to kind of the point where I will say with a straight face that I'll recommend it for production. So this particular workshop, I hope you've had some Clojure experience. I won't exactly be explaining much of the Clojure semantics, but I won't expect that you've even heard of core.typed, except maybe if you came yesterday. I think that's the case with most people. But probably the case is they've heard of core.typed, that sounds cool, but they haven't tried it yet. And this is one of the first kind of extended talks of core.typed, so I would love some feedback of this sucks. Please tell me everything sucks and I'll improve it. So first of all, this workshop's going to be me and Vim, so just the whole time. So what we're going to do, we're just going to check out the type syntax and how the typing scope works, and some of the special types in core.typed and how it integrates with Java, because Clojure runs on the JVM, so it has the same. At runtime, they're all we have classes and references and these sorts of things. So how's that look? Rainbow friends, probably not a good idea. So the first kind of half of this workshop is going to be kind of weird because I'm going to basically emulate a REPL environment when really the way you use core.typed is you get your full namespace of code and you add annotations inside it, and then you run a top-level function called checkNS. And then the checkNS takes a symbol, which is the namespace you want to check, or if you don't give it a namespace, it checks the current namespace. And this is, you can imagine you're working in a REPL, adding stuff to your namespace, and you can just call checkNS, and it'll tell you, it'll give you your type checking when you need it in your REPL. So it integrates quite well with REPL development. And why this particular file is kind of weird, because this is not actually a typed. This is not actually typed code. We're using a macro called CF, stands for check form. Basically, what it does, here's an example. It takes a form and optionally an expected static type, and it blows up if the form is not of that type. And if it is of that type, it just prints it out. So it's kind of a debugging, exploratory kind of way of working with core.typed. Cool. So a bit of Clojure semantics. Clojure, when you write 1 or 1.1 or a number literal like that, we get longs and doubles, and core.typed understands this. So if we try and say, all right, so check that 1 is an integer, we get a whole bunch of redundant type and errors, which I will fix. But usually when you get more than one type error, just in general in any language, you usually want to look at the first one. And there are research languages that actually just, like for students who are learning programming, that just have the first error in it. It's quite useful. But anyway, let's just ignore this. Yeah, and sorry about, when you use this CF thing, the line numbers are a bit screwed up. But you definitely get good line numbers when you do it with checkNS. But we can see that we're expecting a type of integer, and we get a value of 1. And that is a type error. But if we say, okay, we want a long, and it's down here, we're subtly saying, okay, it's a long, that's fine. So the way the scoping works with types is that it reuses the way Clojure scopes classes and vars and things like that. That's basically it, really. You can see I've got an import statement here, and what this import statement basically does is that if I type seekable in my namespace, it refers to Clojure lang seekable. So Clojure, every Clojure namespace comes by default with the equivalent of import Java lang star in Java. So all the Java lang classes are in scope here. So this is actually Java lang star. This is Java lang integer, and you saw it outputted long, but that's just because it prints it out the prettiest way it can print in the current namespace. So Clojure itself is implemented in Java using interfaces and abstract classes, and it's just normal Java stuff. It's not implemented with protocols. So what basically I've done, I've taken the classes, like, if I can get a look back at the imports. These are the kind of things I'm talking about. So there's a seekable class, a seekable interface for things that can be turned into, but things that can be, what's the word, you can create sequences from them, immutable sequences. So because it's immutable, we can parameterize it by one parameter, which is covariant in its parameter. That basically means that we can say that a vector of 1 and 2 is a sequable of number, even though it's a sequable of longs. So that's because this vector is this vector is immutable. No, sorry, it's because the sequable that will be immutable will be immutable. So we also look up the type environment. We use, I think I've got a call somewhere. So you get a bit of perspective on the type hierarchy in Clojure. If we've got an interface called IPsys vector, and Clojure actually extends. IPsys vector extends these things, and you can see there it's Clojure lang seekable. So actually at runtime, I suspect it is a Clojure line sequel, and this basically emulates this. So there's a bit of, it's kind of like Java generics in that you just put some extra generics on top that don't affect runtime or anything like that. But I don't actually attempt to comprehend Java generics in core.typed. Otherwise, I probably would have got nothing done. I've just been staring at a screen all year, doing nothing. So here's a list. We know that's a sequel of number, and that's okay. And of course, this is where, remember up the top, they're in scope because of our imports. Just normal Clojure stuff. It reuses a lot of Clojure concepts. And we've got our set syntax. That's an I-persistent set. Okay, we've got symbols, keywords, and strings. Kind of similar concepts, but they're not parameterized. They're just normal normal classes. String here is a Java lang string. Remember, this is Clojure lang symbol and Clojure lang keyword. And actually, typed Clojure can also supports a type called a singleton type. It's basically a type that only has one member. So a singleton type could contain just the symbol A. So we could say check the form of A, and it'll say it's a value that's a symbol of A. And this is not anything sophisticated. It's just something small. But just a note on this syntax: if there can be multiple kinds of type information that come from an expression. Some of it is to do with its runtime type, and this one in particular is to do with its truthiness. And this particular map here will tell me what will happen if I pass this value to the conditional position of an if statement. And this basically says that if I pass this value here to an if statement, then I will always go down the then branch, and I'll never go down the else branch, which conforms with Clojure's idea of truthiness. And in Clojure, only false and nil are falsy, or false values. So yeah, we've seen all this before. So something with a bit more interesting type is an atom, and an atom is a mutable. Yeah, it's a mutable value in Clojure. And just kind of as an experiment, I've split all immutable types to have two parameters. So usually you have the parameter. If you're doing this in Scala or Java, say, you have one parameter that is invariant, right? So instead of having one parameter that's invariant, I've split it into two parameters. One is contravariant. Well, they're both going in different directions. Basically, the read parameter is here, the write parameter is here. It says, this atom can read this, and it can write that. And it just the way it's set up there is it's basically equivalent to having one invariant parameter. But of course, the most common way you want to use it is as an invariant parameter. You don't really care what the difference is. You don't really have a difference between what you want to write and what you want to read. So we have core.typed supports type aliases. So there's a type alias here. You can see this t/, which is the normal namespace alias core.typed as t. So there's and this is actually a var. So this will result an alias is a var in type Clojure. So I could also refer that here. But in any case, basically, atom1 is the same as atom nn. And more concretely, that's a bogus example. But we could say that this particular atom here, treat it as if it's an atom that can both read and write atoms. And that's basically the most common way you'd want to use it. And yeah, the reason I've split it out into two parameters, core.typed comes with a kind of it's not really experimental, but I haven't really seen it used in other serious languages. But I try and provide a solution to array covariance in Java's array covariance, basically. And it comes down to if you're getting an array from Java, you don't know anything about it judged from its type, and that's because of array covariance. And basically, what you know is that the gist of it is if I get something from Java, I can't write to it, and this kind of type can this atom can express that. So basically, when you get an array that you don't want to write to, it's an atom of nothing, which is the bottom type, so you can never write to it, and whatever the component type is, the same number. So that also means that we can write a function that that can abstract over all. Say, it's probably easy to write. Oh, I've got an example somewhere. Oh. So we have this sum function here, which kind of looks like a sum function you write in Java. You just say, okay, this can work on all arrays of numbers, right? But in this case, it's statically sound because we're saying in this body we cannot write to the array, so there's no way we can mess with the context. So basically, what's happening up here? Anyway, this is the array constructor that does both the read and write parameter. So this basically says my integer array can both read and write integers, and we can pass it to the sum, even though this is not a read and write of integer. It's still statically sound to pass this here because there's no way to change the contents. It's kind of technical, but yeah, that's kind of I've taken that concept and applied it to everything that's mutable in type Clojure, just as an experiment. As long as we have type aliases, it seems to work pretty well. We have the seek function. Something interesting here. That the seek function only returns nil if the sequence is non-empty, right? And it knows, core type knows that this is a non-empty sequence, so we can assign this the type of iseq number. And in core types, we actually very strictly separate nil from everything else. So this is kind of a smart thing to know that this is going to be an iseq. This is basically saying this expression can never be nil. So we've got some functions right now are kind of a corner case, a special case. There is a function type and a function interface in Clojure, but I'm not using it right now, basically because I've inherited some cruft from typed racket. But there are a couple of ways to write functions. Here's the untyped version. It's just a function that takes an A and adds 1 to it. So to annotate the parameters of that particular function, we change it to the fn arrow, which is a var in the core type namespace. We can annotate it with this keyword, and then put our types and just generalize. If we have more than one parameter, we can go like that, or etc., etc. So the return type there is inferred. So if we want to do a more expressive type than just giving the parameters, we can also use CF. So I should probably clarify something. There's a way to annotate a form, an expected type for an expression in core typed, and it's basically like this. So this particular form here is basically equivalent to this check here. But anyway, this anonymous function here is exactly the same as this basically. And this is the way to annotate anonymous functions in core type. Just give them a full function type. And the way to read this is the domains, the parameter types are on the left of the arrow, and the range types, the return types are on the right. And there's sometimes some extra stuff on the right of the range.
You say the syntax inferred on plus, is that something figured out? So
yeah, that's figured out because basically the way that local type inference works is kind of top down, and where we're coming from in here, we're gathering the type of A, and we don't need to backtrack to find to infer any more complicated types. We already know the type of plus.
Okay.
We already know the type 1 of A, so we know it returns a number. So it's going to be, yeah, I think it's going to be the same type as this here inferred.
I'm just wondering what plus, how do you know it?
So I have a set of base annotations for the Clojure core library. Plus is kind of interesting because it inlines to a call to Java lang number /add, which is a method. So that I know about the inlinings as well.
So when you fire a Clojure core.typed, you're getting some of those annotations in the core already?
Yes, but they are unchecked. They are basically, I'm trusting the Clojure core. Yeah, I've done my best to model them. Yeah, it'd be pretty inefficient to check the whole library every time. That's pretty basic strategy with type systems of this nature, at least. So we can get a bit more elaborate with our argument types. We can say we can express a function that takes any number of numbers, and we just use this regular expression like star, and the type to the left of it can occur 0 or more times. So yeah, this function takes any number of numbers, returns a number, and yeah, you can see that the body will. I think that's type correct. Yeah.
Just suppose you compile as it is. Just the element section in the slots of the same object.
In the what?
In the star, next to number.
Oh. Yeah, it has to be a vector.
Oh, right.
Yeah.
Oh, yeah, sorry.
That's all right. This is pretty cool. This is something I added recently to support for keyword arguments and all the nuances of destructuring. And I'm not sure if there's anything I'm missing with destructuring, but I'm pretty sure I support almost all of Clojure's destructuring capabilities. But what this is doing, it's saying that to express some keyword arguments, you put the ampersand symbol, and then you can put a hash map here, and this is the optional keyword arguments that you want to pass to this function. So this basically says that this A here and here could be nil, could be number, and you don't necessarily need to supply them. So if I was calling that function, let's say it's f, this is a valid way of calling it. And if I wanted to say that all the arguments were mandatory, pretty sure I've got another version here, and this syntax may change. It's kind of a bit ugly, but you're basically saying I've got no optional keyword parameters, but I have 3 mandatory ones. You have to supply numbers for these 3 keys, and these structuring calls, they're all Clojure. You don't need to add anything from a core types perspective. And we have these dotted types, which I might get to later. So a very important aspect of Clojure is the ability to use heterogeneous maps as kind of ad hoc objects, and not having to declare things in advance. And of course, this is pretty important to support. So there's support for heterogeneous maps. And what a heterogeneous map is in this context, it's basically a map with known keyword keys. And it can also know, it knows which keywords can be in the map, and it knows which keywords can't be in the map. And those are, two things are useful in different contexts. But we can show the types here. If we type check the empty hash map, it knows this is just a bit of pretty, I'm not sure if there's a way to express this directly in the types. This is basically saying that this is a complete hash map, in that all the keys that are present in here, that's all that's in there, and it's empty, obviously. So we can try the next one. So now we know it's a complete hash map, doesn't have any keys, but it has an A to a value. And remember, this particular, this is actually sugar. This is sugar for this. I should start here then. So we have the HMap constructor, and you can give it either mandatory or optional keyword parameters. And it's kind of like the keyword. I'm using keyword parameters in different contexts. So this sort of syntax, remember this, we have the mandatory and optional. So we can express this as in the HMap constructor and say we expect this form to be the HMap that has an A key that's a number, and this you can see that it infers it to be a partial HMap. Basically means that we don't know if there's any other types in it. There could be extra entries in this map. Yes. So that basically means I know that this will return nil. And let's cross our fingers and try it. Yeah. So if I annotate it to be a less precise type, to get rid of the knowledge of the absence of keys, right? So let's say we only know, yeah, mandatory number. So we get back a less precise type of any.
I was thinking for a moment there that you could say,
yeah, sorry, I don't seem to stop for questions very well, so please just shout out. I get a bit excited, sorry. Yeah, we have some basic support for assoc. We can assoc onto maps, and we can track that we know that it's a complete hash map here, because we inferred this is complete. Therefore, if we add a B key to a complete map, we get a complete map with just a B. We can also do this little trick of threading through and looking down a path of keys. So you can see here, this particular map has a path from A to B to C, and core.typed can follow that. Get our prize at the end. Similar kind of story for heterogeneous vectors. We've got another type syntax, just put a quote in front of it, and the quotes in that are not for the square braces, they are singleton types. So they are a sugar for this particular constructor for value 1. So that's just another way of writing with the tick. So you can see so many vectors. So the type starts here and ends there. So you can see we've got a heterogeneous map. This has been inferred from nothing. But yeah, we've got a heterogeneous map of 3 entries with these 3 values. And we can call nth on them, and it knows get on vector on vector. Oh yeah. This is a little node for me to complete some implementation of that. Basically, get doesn't work here, and it should. I've hard-coded maps to work with get. But you can see we're getting the third element here, and we get back cheese, as you can see down the bottom. So here's something new if you come from Scala or Java. It's a general union of types. And it comes in pretty useful in Clojure because it turns out this is kind of how we think about Clojure. We start off with a pretty general type. We can use type predicates to make it more refined. And we know maybe at this point in our branch we're at a particular type, but maybe if we want a different branch we're at a particular type. But we don't necessarily always have to create new bindings. We might work with just a binding called A, and we might want to use that A all the way through our conditional. And we want to know better types for that A. But in this particular example, we can see that it's valid to make a symbol to be a union of nil symbol and keyword. If this is a symbol, we can just give it a bit less general type. That's it. I'll go over unions a bit later. We have intersections, which I don't think is a good idea to show because they may go away very soon. There's little tricks where I know whether a sequence is going to be empty or not. It's kind of a neat little idiom of Clojure. We can call seek on a sequable, right? And the result is either going to be nil or it's going to be a non-empty sequence, right? So we can see that if we go down this branch, then it's not nil, therefore, imagine if we had a union, it's either nil or a non-empty sequence. Is it nil? No, so it's a non-empty sequence. So if we call first in it, we're going to get back a number. So if the actual refining of the type only matters down this branch because we just return 0. So the gist of that is that we can say this expression must return a number, and it does. So we've inferred that.
Is that because the vector had numbers in it?
Yes, because my seek here, it's a union of nil and a non-empty seekable of numbers.
Okay.
Could be a bit more accurate. Non-empty I seek. Yeah, I think that's what it is actually.
So you've got thing that knows an if loop, it looks at what my seek is and it's going, okay, it's going to go down the true value and go down, okay. First of my seek is going to be number, therefore it's different from number.
Well,
sort of, I mean, just
there's two branches here.
yeah.
But yeah, the interesting bit is in this call here. How do we know that my seek is actually not nil here? It's a combination of unions and occurrence typing, which we'll probably look up pretty soon.
But it's something other than a number in the else branch, would you get a union type back? If it's like that expression?
Yep, so we'll either get 1, 2, or 3 back. This is not as impressive as it looks, really. It's just a bit dumb. Because this ends up being a union of 1, 2, or 3 in its component type of the IC. So yeah. Could be a bit cleaner with the generalization of types in this case. So type Clojure also supports polymorphism. Java has f-bounded polymorphism. That basically means that we can have our type variables and they can have lower and upper bounds, and they can also have recursive bounds that refer to the type variable being bounded. Turns out that lower and upper bounds aren't quite as useful as I thought they would be. I can't pinpoint the exact reason, but because we have unions and intersections, it just isn't as important as in a language like Scala. Lower bounds in Scala are sometimes very useful, but not so in core.typed, so probably won't show you how to do them. But here's the identity function. We have our binder of type variables, and the all type constructor takes some type variables and a type and then scopes the variables in here, as you'd expect. So Yeah, so that's just a simple identity function, and we can. Let's not bother. So we have type aliases. Here's a simple one. Let's just. I've got my own custom integer type. That's just a union of long integer. Yeah, that's simple stuff. But if we want to have a parameterized alias, we use a type function, which is a function on the type level. So it's a function that takes a type and returns a type, or at least it takes a number of types. So in this case, this type function takes a type x, and its variance is covariant, and it returns an isomorphic list of x. And the variance annotation there basically means that a list of integer is a subtype of list of number. Yep. And we can. It's a bit funny that you have to wrap this in CF as well, but basically core.typed has a pretty strict phase of collecting types. And whenever you do annotations, whenever you have aliases, you have to pass it to the type checker somehow. It's not good enough just to evaluate it. Just kind of even I get stuck on that sometimes. Yeah, if it's just normal usage using checkNS, you have ways of specifying types dependencies to different namespaces. So collect these types first. Basically, the way it works is phase 1 is collecting types, so it goes through the whole code base of its type, and then phase 2 is checking it. What am I doing next? Okay. Any more questions? I think this is a type namespace. Yes. You can tell it's a type namespace because CF isn't absolutely everywhere. This is what real core-type stuff looks like. You have your normal Clojure code here, and then you have your annotation. Doesn't necessarily need to be there, but I like it because it fools me into thinking I'm using like Haskell or something. Something awesome. Type bracket actually has more Haskell syntax here, but either way. So yeah, we're annotating food, which in this context, if you annotate just a unnamespace symbol, then it does the obvious thing of qualifying it in the current namespace. So we basically use this type as an expected type for def in here. That's pretty important because in Haskell we have inference, but in Clojure, in type Clojure, we don't have global inference. We have local inference. So basically, the rules are that you need to annotate all vars that have been used in the type namespace, and you also need to annotate the parameters of local functions, which we saw a bit before. Yeah, that last point's a bit annoying. Like we have functions. It's like we can write local functions where you're just staring at it. You're like, why can't you work out what the type is? But the algorithm isn't quite up to scratch at the moment for local type for inference of local functions. But I don't think we're going to get very far. I don't know, in the next few years of getting rid of these sorts of annotations in the top level ones. I think it's pretty good to have these here. It kind of makes you think about stuff, which is it's always good. So you can tweak the ways you can tweak what core.typed actually checks and what it doesn't check. So yeah, and it tries to help you not shoot yourself in the foot. So we have this awful backdoor thing called TC ignore, which basically means, look, my library's in 0.1 right now. There's going to be stuff in here that I haven't handled yet. Just use this liberally when you need it until I support it. So we accidentally wrap this in a TC ignore. So what's going to happen is type Clojure is going to grab this annotation, add it to the annotation of the type environment. Then we're going to come across to this call and we're going to realize that we haven't checked the annotation, and hopefully we get a yeah, so that one at the top, warning definition missing and forgot check. So it's not a type error to not check a definition, but you get an ugly warning. Clojure core iterate. Yeah, so if you don't care about checking the definition, you can use this no check metadata, which I'm just about to do for iterate, because we got that ugly warning before. As I was saying before, the core bars are not checked. So and something also interesting, we can add our own types. If we're missing types, we're gonna be missing some types when core types is early in its development, like iterate. It's a pretty common function, but I had to add it here. But it's as easy as this, really. You just add no check, and then if iterate takes a definition, right? Yeah. So it takes a function and an initial a function from x to x and takes an x, and then it produces a lazy sequence of repeated calls, recursive calls to that function. And you can use it like this. You can give me 30 indications of this particular. Sorry, give me 30 items of this lazy sequence. And this is just showing. This is not always a good thing. This no check metadata here, because we're saying assume it's a number to a number, but it's nil here. So a bit of give and take there. A bit of flexibility, you can really get into trouble. But here's there's a problem in core.typed in that you can't infer local arguments, local lambdas, and you can't infer local loops. You need to add extra type annotations. So that basically means any macro that uses like loop, for, do, seek, do times, and basically every macro out there needs to have a wrapper. And this is a particularly awful one because this is the actual code here. So A is going to be a bunch of numbers, and we're going to say when it's even, then we're filtering on even, basically, yeah. So what the first thing we need to do for a for loop is to give the return type of the member. This is going to return a lazy sequence of stuff, and this is the stuff in here. It's going to be giving back any integer. Any integer here is an alias. Basically a union of Java lang integer, long, big int, Clojure, big int, or whatever it is. It's basically everything that returns true if you pass it to integer question mark, Clojure core integer question mark. Yeah, and it's kind of helping me delay working out how numbers work in Clojure as well. But in the for loop, we need to give two annotations, two types. Give the return type and the type of the A here, one of the loop variables. And we're saying that A is going to be in any integer inside this loop, and we don't need to annotate the when because this actually expands out just to a normal when. But something interesting, in this particular core type knows that that's not interesting. I don't want to. I hate these macros. I promise I'll do something about them. But here's do seek, same kind of thing. Do times is hilarious because you just don't need any annotations, but you need to do the arrow anyway. Yeah, all of the type racket has like 200 loop forms. It's pretty hilarious. There's like a for loop for every single kind of sequence, and Poor guys, yeah. Yeah. It's not quite that bad, but there's a lot of loops. There's not just for and do seek in loop. Yeah, so loops are a pretty important one. I think this is going into a bit more detail here. So this code's basically doing nothing. It's taking code. It's taking the numbers from the n list and just adding it to the accumulator, and it's going to give back a vector of 1, 2, 3. But I'm going to use it to demonstrate, I don't know, an interesting invariant core.typed has. Okay. This is a problem. I cannot see the code. Alright, well, yeah, this isn't the easiest thing to read, but basically what's happening is, thank God I can see the function name, but we're calling Clojure core next, and the actual call is here, Clojure core next. This is the fully macro expanded form that we're checking here. We're giving it the n list, and for some reason I've given the next form just for good measure. But basically what this part's saying, Clojure core next, its type has just has one arity. It has an arity that accepts an option seekable x. So this option, all it is, union, nil, and that. Right? So it's our make-believe option type. It's kind of what we think of as an option type in Clojure when we code it. So we can either give this nil or a sequel of x. So what do we give it? Yes. Okay. So this needs to give you a bit more information because next actually returns nil, or it could return the next sequence, but we're expecting a sequel of number. Yeah. So it's kind of it's a bit anal at that point. Seek. Another to do. Any questions? All right, let's dig into everything about nil. So nil is not very useful in core types. It's not a seekable. It's not a list. It's not an object. It's just nil. And that's basically all there is to it. We do have a top type called any, and the way this is, because of these facts here, we can actually guarantee that type code does not have null pointer exceptions, which means that we can give a type error if we do something like this. We can say this is always going to blow up, or even if it's a union with nil in it, there is potential for it to blow up here. So we give a something like cannot invoke nil, which is a pretty cool error to have on the JVM. And yeah, it's the same sort of thing here. But yeah, it's not like in Common Lisp where nil is a list or anything like that. It's really, and it's not like Java either, because anything could be nil in Java. So really, I've tried to isolate the problem as much as I can. And we can guarantee we don't get null pointer exceptions in certain parts of our type code. Yeah.
Just a question on any there.
Yep.
You're running a check on your namespace. You haven't put an annotation for anything. Would that basically be an any?
So the rules are, if you have to give a type for a var, but if we have a lambda or an anonymous function that doesn't have we have one right here. If we try and run this, then A is going to be any here. We're going to at least try it out. The reason is because we can understand things like this. We can use Where's my friends gone? I wonder if this is going to compile. I'm going to type check. Oh, type system map. I have no idea where that's come from. I've got some state somewhere.
But what you're saying is that any is just a figure of lambda k.
Yeah, so the A here is going to be any, but the interesting thing is we can do a lot with that any by kind of casting it, but not really, by using assertions and conditionals. Yeah. So there's some ways to debug our type code. Is that clear about nil? Everyone happy with it? Yeah. Cool. All right, so we have some ways of debugging our type code, or making it, or putting or static assertions in our code. So here's the weirdness of having to put CF around and. So this adds an annotation for number function here. So basically here we're going to print the type environment at this point. And I hope it's not too ugly. Print env. Alright, why am I, okay. I'm just gonna, something really weird's happening. I'm in the wrong namespace. Silly Vim. Oh. Debugging. Oh, it's still in the wrong namespace. Oh well. Why is this not working? Let's move on to static assertions then. Oh man, it's so small. Font. Oh, it's a bit small. So this is kind of like a precondition, but at compile time, right? A type precondition. And basically, this is going to blow up at this point, or is it? No, it's not, because we've annotated number function. Oh, yeah, it is going to blow up. A is going to be n here, so this is going to basically say that A is not a number. But you have code like this. So I had some code, I wrote for an assignment I wrote a cellular automator that had a grid. It was represented as a vector of vectors. Then I changed it to be a map with a keyword grid with the grid inside it. And basically, I had an assertion in here that said that the grid is going to be an I vector, an I-persistent vector of I-persistent vectors. And once I changed the code of the, all the functions. Once I changed the type of the grid, all the functions that consume the grid complained basically and told me exactly what I needed to change. That's just one way of making your code a bit more robust. I wish this worked. It's not working. Over time. Half an hour. Alright, so we're going to move on to occurrence typing. So occurrence typing is the way that we infer better types for local variables as we progress along our code. And there are two aspects to occurrence typing. One is to attach filters or propositions to functions. You can see this single question mark has, it looks like a normal function, takes an any and returns a boolean. And then we have this funny thing here, which we saw before as the what is true if this if we go down the then branch, if we pass this expression to an if statement, and what is true if we go down the else branch. So if we have something like a symbol question mark a, then this 0 is referring to this any here, this first parameter. So a comes up and replaces this. So then this particular expression, if you pass it to an if statement, says then if we're in the then branch, then a is a symbol. If we're down the else branch, then a is not a symbol. And have another one of these functions that has a conditional, and we don't actually know anything about a at this point. We can return a symbol. So the first case, symbol question mark, updates the type of a at this point. So this returns a symbol. And then we have string question mark, and in here we know that a is going to be a string, and it just so happens that symbol takes a string. So this is type correct. And otherwise, we don't know very much about it, so we'll return an unknown. It's kind of a contrived way of demonstrating how these filters are being used. Any questions on that? So we don't always have to use conditionals like this to take advantage of our propositions in occurrence typing. We can also, as we saw before, use preconditions. This just expands out to an assert. And it's like the first statement would be this would be in a do, this would be assert number question mark. Basically, core type knows that if we're at this point, either we've already blown up, then we don't need to worry about it, or a is going to be a number. So we can use these propositions from this particular expression downwards and also kind of inwards. And that's an improvement, enhancement from typed rackets implementation. Sam Tobin-Hochstadt, the author of typed racket, conveniently told me how to do it, and it was very easy. I'm very glad. I'm glad he proved it all for me, and I just took all the credit. Fix me. No. Bars. This is kind of surprising. Core type really is very strict about whether a particular thing is mutable or not. So a dynamic var in Clojure is mutable. You can change its value, but usually what you do with a dynamic var, you bind it and then you just assume that it's immutable as you go down. But unfortunately, core type doesn't buy that. So this kind of expression is actually not correct, because there's no filters on a mutable structure. We don't know that if we've gone down the then branch testing that a mutable structure is not nil, we don't know that it hasn't changed at this point. So the key to occurrence typing working in this case is this particular expression being immutable, that it cannot change. But of course, v number is a var, so according to core type, it can change. So it ends up, whenever you have this sort of idiom in here, you have to use a when let. So basically convert the mutable structure to a immutable one, to a local binding. And now what this when let does, it actually tests the number. And we know in this. So this should, yeah. You see the bug? Oh, this isn't going to work, is it? No, my Vim is not working. But the bug is, obviously, I'm assuming that this whenlet has defined the type of the number star in here, but it hasn't. What I should have done is use the local immutable binding here, and this would please the type checker, basically. Yeah, here's something cool. So I've ported some of the contrib library algo monads, which is a way of using monads in Clojure. Where is it? Monads. And there's a cool little thing where we can combine macros and declaring types, basically. So turns out that if we have I've actually forgotten the details of this, to be honest. This was for my dissertation last year. But the idea is that a monad function has a bunch of implicit parameters. This looks like a bind, a return, something like that. And this is the star one. It takes any number of functions. But this is kind of internal to the way, to how you use a monad function. All we care about is the M here. So you can see that we're actually writing an monad function here. This is this particular definition here. And we're actually giving two types. This type here is a bit of boilerplate to please the nuances of, what are they? The local macros, that library, tools macros or something like that. But there's a way of having local macros, and it ends up you have a particular binding for mjoin. So that annotates mjoin. We also annotate the function. So this particular binding here, really what's happening is we have like five arguments behind here. So we put them in automatically at this point, and we annotate them. And what ends up happening, we have two annotations that are generated with macros. And yeah, this is just showing how we can use macros to generate types and to kind of get them out of our way when we know a bit more about our types than usual. Any questions on that? I'm sorry, I've completely forgotten the details on that. I just remember that was cool. I liked it.
Does it help you implement monads to have more type information about them?
I've been thinking about that recently. I don't know much about that. Yeah. The next step for me with monads is trying to type check Jim Dewey's library, the protocol monads. Yeah, but basically the inference is not good enough in Clojure to even hope of doing something like Haskell, because we need a dispatch on the return type of things. And core.typed doesn't even change code, let alone know what the return type is going to be. So there's a few things that need to happen. We need an extensible Clojure compiler, and then we need some amazing research.
And then we get Haskell.
Yeah, that's it.
Yeah.
So type Clojure, core.typed, whatever you want to call it, is integrated with Java. We can use Java interop freely. And basically what happens is let's get rid of these lines. We know the types of methods at compile time just by looking up the Java types, basically. And there's a few assumptions that we have about Java, interactions with Java. Basically, when we call a method from Clojure, a Java method, if there isn't anything special, we default to not allowing you to give a nil value to a parameter. And we always assume, so we're very pessimistic here. We assume that we're getting back something that could be nil. Constructors are a bit less restrictive because constructors, as an invariant of Java, that they can never return nil. So we know that if we call a constructor, we're going to get a not nil value. And the same with the parameters, same restrictions there. And the fields, anything goes with fields. So I'm just going to show you a bit of code that uses some Java interop. So this is part of my cellular automator. And basically I'm using GNU plot to plot my grid, my lattice. And this particular function, it just starts up a process for us and gives us a lightweight map to work with here. And out here is going to be the output stream of the GNU plot process that we can just throw things at it. And then proc is the actual process. So first thing to notice is that we've abstracted out the actual details of what this is going to contain with the GNU plot P. I guess it's GNU plot process. So it's going to be a map with a proc P, that's a process. This is Java IO, no, this is Java lang process. Okay, it must be a Java lang one, thanks. And we have writer here, and that's Java IO writer. But the interesting things here are these 3 lines. And the reason we have to, we know that, I think, that if we call Java lang runtime, get runtime, we can't get nil, basically. And what this all is saying is for all arrays of get runtime, and there may only be 1, but at this point, you can see here we're actually calling it. And the problem is that we're calling exec on it. So if we assume that it was going to be nil, that's a runtime, that's a compile time type error for type. So we need to add this annotation. And this is a kind of, you end up with an interesting, you end up accumulating a whole bunch of assumptions about Java code that you put in real code. It's not in a comment, it's machine, well, I'm not going to say it's machine check, because you can't check the Java, the actual Java, but these are definitely just assumptions. You're kind of directing core.typed to be as useful as possible. So we don't want core.typed to blow up at this exec, because we know that get runtime is never going to blow up. Sorry, to return nil. And we can do the normal calling of constructors. So we've got the output stream of the process. We can do everything you can do in Clojure normally. And yeah, this is a combination of, I guess, interop and H-maps. So our H-map here, we know it's a process, so this is always going to resolve properly. Any questions on that? There's also nillable param, which is another directive to say this particular parameter can be nil. And there's another one called override method, which just you can do anything with. And yeah, it's kind of an internal thing, but you can definitely tune the way you can tune how useful core type can be with Java interop. So of course the big hole here is that what if get runtime actually returns nil, and there's basically nothing we can do about it except extend core type to add a contract, a runtime contract. And typed racket does this sort of thing. So you'd actually need a way of inserting a contract around here, and there's currently no way to do that with the compiler, so I haven't bothered to even try. You can annotate data types and protocols, and I guess the crucial thing to understand here is I can only check what I can see, right? If we start, the guarantees that Clojure, the core type gives you are only valid at the time that you run it, right? If you start implementing this protocol at runtime and you don't check it, then you can't really do much for you. So that's basically the scope of how much core type can help you with respect to dynamic loading of code. So it really, it doesn't help. Something funny here with protocols, it's another one of these arrow functions where we don't actually understand the macro expansion, but doesn't actually add anything to we don't add annotations. But the thing that's going on here, we've got an iadd protocol that adds things, and here's its method. It's an adder, this method here. So it has an implicit first parameter with iadd, takes a number, returns a number, and here's its definition. And so core type does a few things at this point. It adds the annotation for the protocol, and it adds the annotation for that var. So there will be a typed workshop data type / adder, and this var down here will have that type up here, as you'd expect basically. And we can, whenever we implement the protocol, it makes sure that it conforms to the type. But annotating a data type, all you need to annotate for a data type is the type of its fields. So this is the same sort of syntax as the FN arrow, where you just have a comma and you have a couple more annotations. But yeah, so you can see and data type also annotates the Java constructor, the adder dot. It also annotates the array of the arrow adder. It also annotates the map arrow adder, which you can supply a full map to it. So it tries to be as helpful as it can for annotating stuff. That's about it with protocols and data types. Any questions on that? Multi-methods, a blank slide. This is scary. This is I really like this. This is really cool. Just, yeah. So I've always wanted to type check the Clojure script compiler. I think if I sat down, I could probably do it at this point. I've done enough work to get it done. I just need to sit down and do it again. Wow, my computer's slow. Oh yeah, I'm showing you multi-method. So this is kind of where multi-methods and occurrence typing meet. So this is a multi-method that takes one argument, and I've actually annotated the expression, and that massive type annotation that you saw before that I tried to hide, that is an expression. So it's basically a union of an if statement, a lambda, and all the primitives. But basically we take an expression and then we return nil. So emit has some side effect. So the interesting thing here is the methods, the consumers of this dispatch function. So the dispatch function here is taking an expression and then returning the op. And we can see if we go back up to the type of expression. So expression is a recursive type where x is the expression. For example, here's the if statement. The op is the value if, and then it has a form, which I think form is just any. We don't know anything about it. And then test is an expression, then expression, blah 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 blah. Then we have throw, try it, and all that. But the idea here is if we know that op, if we know that looking up op here gives us if, then we know that everything else isn't valid at this point. We can safely update it to only be this map. That's basically what happens in the methods of emit. Yeah, so for example, in here, core types can infer that this particular argument is going to be an op map, and it knows things about the end, simple keys and values. Right now, this support's basically limited to what that can, to just a single, to a dispatch function that takes, no, it's limited in what the dispatch function can return. So the dispatch function here returns a keyword, right? We can also, if we wanted to do like multiple dispatch, we could return a vector of, of classes, and then we could use ISA to dispatch on that. And core typed isn't quite up to that at the moment. Oh, I got 5 minutes. Any general questions on core types? Yep.
A lot of people who like type systems, fans of Haskell and Scala, often describe the experience of using the type system as a tool to design programs correctly. Is that what, are you aiming to be able to do that with core type, or have you found examples of that? Or does it lend itself better to checking things for correctness, making local assertions about type functions out in the program?
Yeah, it turns out that the Clojure is a bit too dynamic to really be good at that second thing, right? At actually testing the local properties. But yeah, definitely, it's intended to. You can design your program. You just write your types, and then it's a mental model just like Haskell. And I didn't actually see the holes, Haskell holes, hole-driven development. It's not in here. Oh, that's disappointing. Noisy hole, silent hole. Come on, it's got to be in here somewhere. Oh yeah, here it is. So if you haven't seen the whole development, like hole-driven development screencast, it's pretty cool. Basically asking Haskell's type system what's the next thing you need to do, basically. And core type can basically emulate this by having something called a silent hole, which just blows up at runtime, but the type checker just doesn't care about it. It just assumes it's correct. Then we have a noisy hole, which then the type checker tells you, hey, you need to put this particular type in this position. I'm sure this is very primitive hole-driven development, but I thought it was pretty cool. Here's the find type error. And basically, the idea is that these are just local assertions that F is going to be of this type and G is of that type, etc. But if we put a noisy hole in, then core type tells us, hey, we found a hole, but we're really expecting a C. And I think it gets better. No, you basically keep going, moving your holes wherever you want them to go, and then the type system will tell you what types need to go in particular positions. Yeah, I'm not sure how many languages can do that. Like, it might be all of them, but I've only seen Haskell, seen it done in Haskell. I don't even know if I answered your question.
I think you did.
In a way. Yeah. Anyone else? Any other? Yep.
So, is there anything, any benefit you derive from looking at type systems and library?
Yeah, so it's just a jar. You don't need another compiler. You can just use, the secret sauce is macros, basically. Like TypeScript, pretty sure it has its own compiler. And yeah, that's the big difference. We don't need to throw away anything, really. We've already got our compiler. But yeah, I think that's one of the coolest things, that things like typed racket and core typed really are just a package of stuff that you can just add wherever you like. Yeah, that's pretty cool stuff. Yeah.
There's a few things that have been done in my piece that is a bad idea.
Mm-hmm.
One is things known as threads.
Threads.
Like threads of library, for example,
I don't know anything about that, so yeah, I get the gist.
Compiler needs to know threads to be able to insert multiple
Okay.
Is there anything you lose by doing this library?
I give the programmer full power to use type checking where they want and where they don't want, and you could make the type system not be any use at all. So the flexibility of allowing you to use the rest of Clojure kind of comes at a price that, core.typed is powerful enough for you to make it useless, basically. So it's about discipline. If you're writing typed code, you need to follow a certain discipline, just like you would writing in a statically typed language. The type system is there to, I guess, kind of constrain you to a particular set of expressions or ways to program. Just so happens that I've tried to, everything except dynamic code loading is basically what I'm trying to support with core.typed.
Can you make any assertions about whether or not a function has side effects?
Pretty sure that's it. Yeah, that'll do for me. Okay, thank you.